We are going to talk about balanced binary search tree today. First of all, we'll define what is a balanced binary search tree, motivation for studying this, and then we'll talk about AVL trees, which are one type of balanced binary search tree. We will discuss about their properties and the operations, that is insert, delete, and traversal. What is a binary tree? Binary tree is one in which every node has at most two children. When we talk about binary search tree, in that elements are organized as per specific ordering property. That is, the nodes in the left subtree of the root will have smaller values and nodes in the right subtree will have bigger values. When we talk about the balanced binary search tree, it has an additional balancing property. A balanced binary search tree is one where all the branches from the root have almost the same height. If you look at the two different trees mentioned in this slide, the one on the left is considered balanced compared to the one on the right. If you look at the height of the balanced tree, it's roughly equal to log n, where n is number of nodes in the tree, whereas the unbalanced tree in its worst case can have height proportional to the number of nodes, that is order of n. What is the motivation for having balancing in a search tree? When we try to do any operation in a binary tree, the complexity of that operation is order of its height. So if the tree is unbalanced, as we know its height is order of n, and so will be the complexity of operations, that is insert, delete, and update. Each of these operations will take order of n operations. On the other hand, if the tree is balanced, its height will be proportional to or order of log n, and so will be the complexity of insert, delete, and other operations. Let's now talk about AVL trees. AVL trees are named after the Adelson, Welsky, and Landis. AVL trees are the binary search trees with additional height balance property. In AVL trees, for each node, the difference in height of its two subtrees is in the range of -1 to 1. We call it as a balance factor. Before trying to check whether this tree is an AVL tree or not, let us define the notion of the height and the AVL tree node structure. The height of any node in the AVL tree is defined as follows. If the node n is null, its height is considered as -1. If node n is a leaf node, its height is considered 0. For any other internal node or non-leaf node, its height is defined as 1 plus maximum of the height of its left child and height of its right child. As we are required to keep track of height of every node, the AVL tree node structure has an additional field called height. Let's now check whether this tree satisfies the AVL tree properties or not. As we know, AVL tree is a binary search tree. That is, for any node, the values in its left subtree should be smaller than it, and values in its right subtree should be bigger than it. which is very well satisfied here. Let's now check for the balance factor. As we know, balance factor calculation requires height of every node. So let's check that first. Height of 50 is considered as 0 as it is a leaf node. Similarly, height of 75, 80 and 95 are also 0. When we look at the right child of 60, it is a none node and its height is considered as -1. So if we compute the height of 60, it is 1 plus maximum of height of 50 and height of none node. That is, height of 60 is 1 plus 0. That is 1. Similarly, height of 78 is 1 plus maximum of 0 and 0. That is 1. Height of 90 is 1 plus maximum of height of 78 and height of 95. That is 1 plus maximum of 1 and 0. That means height of 90 is 2. Similarly, height of 70 is 1 plus maximum of height of 60 and height of 90. That is, height of 70 is equal to 1 plus maximum of 1 and 2. That means height of 70 is 3. Let's now talk about the balance factor. Balance factor of 50 is height of its left child and height of its right child. As 50 is leaf node, both its left and right child are none and their height is -1. So difference between their height is 0. That means balance factor at 50 is 0. When we talk about balance factor of 60, it is difference between height of 50 and height of none node. That means balance factor of 60 is equal to 0 minus -1, that is 1. Balance factor at 78 is 0 minus 0, that is 0. Balance factor at 90 is equal to height of 78 minus height of 95. That means balance factor of 90 is 1. Similarly, balance factor of 70 is 1 minus 2, that is -1. So as we can see, the balance factor of every node here is in the range of -1 to 1. So AVL tree balance factor property is satisfied.